In this lesson, we are going to learn how to find the arc length and the area of the surface of revolution. So let's begin with arc length. Suppose we have a curve like the one above, described by a function y equals f of x, and we want to find the length of that curve between x equals a and x equals b. So between that point and that point, how long is that curve? So let's start by taking the interval and dividing it up into n pieces. Let delta x equal b minus a over n. So we'll let a be represented by x naught. The next point will be x1, x2, x3, etc. up until you get to xn. And I am going to let p naught be the point on the curve when you plug in x naught. P1 will be the point on the curve when you input x1. P2 will be the point on the curve when you input x2, etc. P3. Okay. Now, one way to estimate this distance on this curve, how long this curve is to approximate the curve on each subinterval by a straight line. So connect those dots with a straight line, connect those with a straight line, because you can find the length of a straight line. Now we are going to let bar pi minus 1 pi, this is going to equal the distance between pi minus 1 and pi. And those look like absolute value bars for a reason. An absolute value is an example of a distance function. So then the length of my curve will be exactly equal to the limit as n goes to infinity, where I add up all these little distances. So from I equals 1 to n, pi minus 1 pi. So this will add up the distance between p naught and p1, and p1 and p2, and p2 and p3, etc. And if you take a limit as n goes to infinity, you're going to eventually get the exact value. So what we have to figure out is how to find the distance between 2 points. So you should know this distance from the distance between 2 points is given by the root of x2 minus x1 squared plus y2 minus y1 squared. It just comes from the Pythagorean theorem. So the point p sub I minus 1 has coordinates x sub I minus 1, y sub I minus 1, and the point pi has coordinates xi, yi. So then what it tells us is the distance between pi minus 1 and pi is equal to the square root of xi minus xi minus 1 squared plus y sub I minus y sub I minus 1 squared. And you'll notice that xi minus xi minus 1, that's like taking x3 minus x2, or x2 minus x1. That's actually delta x. So delta x squared, and similarly yi minus y sub I minus 1 is delta y squared. In order to proceed, we have to make the assumption that f prime is a continuous function. That will be needed later on. And so since we make this assumption that f prime is continuous, we can use the mean value theorem. And that tells us that there is some number, x sub I star, in the interval from x sub I minus 1 to x sub I, where f prime of x sub I star is equal to f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. The thing to notice here is the following. So since f of x sub I star was equal to f of x sub I minus f of x sub I minus 1 over xi minus x sub I minus 1. Notice that the numerator is the difference in y's, the denominator is difference in x's, so this tells you that this is equal to delta y over delta x. Or we have that delta y is equal to f of x sub I star delta x. And going back to the expression we had for the distance between 2 points, delta x squared plus delta y squared is now equal to delta x squared plus f of x sub I times delta x, the quantity squared. Now you can factor out delta x squared times 1 plus, oops, that should be f prime of x sub I star squared. And we can now root delta x, which gives us the square root of 1 plus f prime of x sub I star squared delta x. And that is the length of the piece between, the length of the straight line between p sub I minus 1 and p sub I. Now the exact length is given as a limit as n goes to infinity of a sum of these things from I equals 1 to n of this expression. And by definition, this is an integral from a to b of the root 1 plus f of x, f prime of x squared dx. Now this assumption relied on the fact that the derivative was continuous and therefore this was integrable. But so for any curve, any smooth curve f of x whose derivative is continuous, that's called smooth, the length of the curve between a and b is given by the root of 1 plus the derivative squared integrated between a and b. So the arc length formula says f prime is continuous on ab, and the length of the curve y equals f of x on the interval is given by L equals the integral from a to b root 1 plus f prime of x squared dx. Find the arc length of y squared equals x cubed between the points 0, 0 and 4, 8. So y squared equals x cubed looks something like this. We care about the distance between this point and this point. So I will solve that for y. Y is equal to x to the 3 halves. So the arc length formula says that the length of the curve is the integral from a to b root 1 plus f prime of x squared dx. So let's find f prime. Y prime is 3 halves x to the 1 half. So the length, and these, the a and b are the x values, so we'll have the integral from 0 to 4 root 1 plus 3 over 2 root x squared dx. So you have the integral from 0 to 4 root 1 plus 9/4 x dx. Now you could do a u substitution for the stuff inside the root, but there's a shortcut that it would be useful to know. So that is 1 plus 9/4 x to the 1/2 power. So if you just apply the reverse power rule, we'll have 1 plus 9/4 x to the 3 halves, coefficient 2/3. And just think about that 9/4. If you differentiate, you end up with a 9/4 out in front, which you need to not be there. So if you insert multiply by 4/9, you've compensated and made that so that it doesn't matter anymore. evaluated from 0 to 4. So this will equal 8/27 times 1 plus 9 to the 3/2 minus 1 to the 3/2, which gives us 8/27 times 10 to the 3/2 minus 1. Now simplifying that 10 to the 3/2 a little bit, that's the same thing as 10 cubed square rooted. So that's the square root of 1,000, which is 10 root 10, because 1,000 is 100 times 10. So the final answer you should give will be 8/27 times 10 root 10 minus 1. Find the arc length of the graph y equals x to the 5th over 6th plus 1 over 10x cubed between x equals 1 and x equals 2. So first you have to be careful not to mess up the derivative. So y is equal to 1/6 x to the 5th plus 1/10 x to the negative 3rd. Now differentiate. Y prime is equal to 5/6 x to the 4th minus 3/10 x to the negative 4th. The length of our curve will be given by the integral from 1 to 2 root 1 plus 5/6 x to the 4th minus 3 over 10 x to the 4th quantity squared dx. Now, over here on the side, let's figure out what this expression is. So if I take 5/6 x to the 4th minus 3 over 10 x to the 4th and multiply it by itself, that one's not so easy. So it's good to be careful and do that slowly. So this will be 25x to the 8th over 36 minus 15 over 60, because the x's in the numerator cancel the x's in the denominator, minus 15 over 60 again, plus 9 over 100 x to the 8th. So simplifying that a little bit, we end up with 25x to the 8th over 36 minus 1/2, it's negative 30/60ths reduced, plus 9 over 100 x to the 8th. Now when I take that and add 1 to it, I'm going to have the integral from 1 to 2 of the square root of 25 over 36 x to the 8th plus 1/2 plus 9 over 100 x to the 8th dx. And if you look at this and think about the fact that that came from 5/6 x to the 4th minus 3/10 x to the 4th, the quantity squared, and instead inside this integral we have a plus 1/2 instead of a minus 1/2, the stuff inside the root sign will factor into 5 over 6 x to the 4th plus 3 over 10 x to the 4th dx. That all squared, which is actually pretty lovely because then the root cancels the squared, and we have the integral from 1 to 2 of just plain old 5/6 x to the 4th plus 3/10 x to the negative 4th, which we can then apply the power rule to. So that gives us, when we anti-differentiate, 5/6 times 1/5 x to the 5th plus 3/10 times negative 1/3 x to the negative 3rd, evaluated from 1 to 2. Now we have 1/6 x to the 5th minus 1 over 10x cubed, evaluated from 1 to 2. And when you plug in 2 and then plug in 1 and subtract the results, you end up with 1,219 over 240. That kind of factoring trick will probably often come up in your homework because it's very hard to make problems that work out nicely for this arc length stuff. So there are sort of a limited number of kinds of examples that you can be given that will actually work out nicely. So just be aware of this kind of tricky factor pattern. Let's use the idea of arc length to find the length of the cable in the following picture. So what we have here are two towers that are 200 feet apart, and a cable runs between them. The cable is 150 feet off the ground at its lowest point. So we are going to want to find the length of this cable, for which we can use the formula integral from negative 100 to 100 square root 1 plus y prime squared dx. So let's start off by finding y prime. So y prime will be 75 times e to the x over 150 multiplied by the derivative of x over 150, which is 1 over 150, plus e to the negative x over 150 multiplied by the derivative of negative x over 150, which is negative 1 over 150. Next, we can factor out the 1 over 150, which gives us 75 over 150, or 1/2 times e to the x over 150 minus e to the negative x over 150. Now the next thing we will have to find is 1 plus the derivative squared. So let's just figure out what y prime squared is. So 1/2 squared is 1/4, and then I just have to square the e to the x over 150 minus e to the negative x over 150. So I have e to the x over 150 minus e to the negative x over 150 multiplied by itself. If you're uncertain how something is going to square, you always can revert back to this. So we'll have 1/4 times, now e to the x over 150 times e to the x over 150, those powers will add, giving us e to the 2x over 150, or e to the x over 75. Multiplying e to the x over 150 by negative e to the x over 150 will give us negative 1, because when those powers add, we get e to the 0, which gives us 1. Multiplying e to the negative x over 150 by this one gives us minus 1 again, and then minus e to the negative x over 75. So that simplifies to 1/4 e to the x over 75 minus 1/2 minus 1/4 e to the negative x over 75. Alright, now let's find our length. So our length is the integral from negative 100 to 100 1 plus y prime. So if I take the expression above in red and I add 1, that 1 combines with that negative 1/2 and adds to positive 1/2, and we have 1/4 e to the x over 75 plus 1/2 minus 1/4 e to the negative x over 75 dx. Alright, now let's factor out the 1/4 from the expression inside the root sign. So we have the integral from negative 100 to 100 square root 1/4 times e to the x over 75 plus 2 plus e to the negative x over 75. And once again, there's a slightly tricky factor pattern, but this will factor into the following. Negative 100, 100, root 1/4. That will factor into e to the x over 150 plus e to the negative x over 150 squared. And now you can square root both the 1/4 and this expression, and that gives you the integral from negative 100 to 100 of 1/2 times e to the x over 150 plus e to the negative x over 150 dx. And now when you anti-differentiate, we will have 1/2 times e to the x over 150, we'll need a coefficient of 150 there, minus 150 e to the negative x over 150, evaluated from negative 100 to 100. Now 1/2 times that 150 will make 75, so I will have 75 times e to the 100 over 150 is 2/3 minus e to the negative 2/3, that's plugging in 100, minus 75 times e to the negative 2/3 minus e to the positive 2/3. Now we're almost done. Factor out that 75. And notice we will have e to the 2/3 minus negative e to the 2/3, so 2e to the 2/3. And similarly here we will have negative e to the negative 2/3 minus another one, so minus 2e to the negative 2/3, which we could express as 150 times e to the 2/3 minus e to the negative 2/3, and it's about equal to 215 feet. In an earlier lesson we found the volume of solids of revolution. How might we find the surface area when a line or a curve is rotated about an axis? So consider the following example. I have a straight line with length L, and this distance at the lower side is R1, the bigger side is R2. And we spin that around the x-axis, and I would like to know what the surface area of that is. And what it's going to be is S equals 2 pi r times L, where r is equal to the average of the lower and upper radii. Now, proving that is a homework exercise in your book, so we're not going to do that, but we're going to use that idea to find the area of a surface of revolution. So suppose we have a curvy curve between A and B. And as before, you divide your curve into little pieces, divide your interval into subintervals, so there's x1, here's x2, here's x3, A corresponds to x0 and B corresponds to xn. Once again, as always, delta x is equal to b minus a over n. And you approximate your curve by little straight lines again, just like we did when we found arc length. So little straight lines, etc. And now because those lines are straight on each subinterval, you have one of these objects. Now let's let S sub I be the surface area of one of these approximations. So that surface area will be equal to 2 pi r sub I, where r sub I is the average of the left and right radius, times the square root of 1 plus the quantity f prime of an x sub I star, so some sample point in the interval, squared. And notice that this is your arc length formula. So what you can think is it's 2 pi r circumference times how long. And to find the actual surface area, we would take a limit as n goes to infinity after we add them all up. So from 1 to n, 2 pi. Now one thing to notice also is this r sub I will equal some function value, so some f of x sub I. star. And that by definition becomes an integral from a to b 2 pi f of x times the square root of 1 plus f prime of x squared dx. And what I find helpful to think about this is the following. I think it's helpful to think about this part as the circumference of a subpiece, and this part as the length of that subpiece. If you think about it that way, I think it makes it pretty obvious that you're going to get the surface area this way. So let's do a particular example. So the curve y equals root 4 minus x squared between x equals negative 1, x equals 1 is an arc of the circle x squared plus y squared equals 4. Find the area of the surface obtained by rotating this arc about the x-axis. So we have a circle of radius 2, and we are taking the portion from negative 1 to 1, so that portion, and we're spinning that about the x-axis, and we'd like to find the surface area. So the surface area formula is the integral from a to b 2 pi f of x times root 1 plus f prime of x squared dx. So circumference times your length. Now since we're going to need f prime, let's figure out what it is. So y prime is equal to 1/2 times 4 minus x squared to the negative 1/2, and don't forget your chain rule, multiply by negative 2x. And that gives us negative x over the root 4 minus x squared. So my surface area is equal to an integral from negative 1 to 1, 2 pi, f of x is just the regular curve, so 2 pi times the root of 4 minus x squared times the root of 1 plus this quantity squared. When I square that, I end up with x squared over 4 minus x squared dx. Now let's get a common denominator inside that second root sign and simplify a little bit. So factor out my 2 pi, integral from negative 1 to 1, root 4 minus x squared. Now inside my second root sign, I will have 4 minus x squared over, or plus x squared over 4 minus x squared dx. Those x squareds cancel, just leaving me 4. So I have 2 pi times the integral from negative 1 to 1, root 4 minus x squared times root 4 over 4 minus x squared dx. And you'll notice that when you root the numerator and denominator individually in this expression, this will cancel with that, leaving you just the root of 4, which is 2 dx. Now the antiderivative of 2 is 2x, so we'll have 2x times 2 pi, that's 4 pi x, evaluated from 1 to 1. And this gives us 4 pi minus negative 4 pi, or a surface area of 8 pi. Next, let's find the area of the surface obtained. We rotate y equals 1 plus 4x square rooted about the x-axis between x equals 1 and x equals 5. So first let's find y prime. Y prime is 1/2 1 plus 4x to the negative 1/2 times 4, or 2 over the square root of 1 plus 4x. Now the surface area will be the integral from 1 to 5 2 pi f of x root 1 plus f prime of x squared dx. So in this particular case, we'll have an integral from 1 to 5, 2 pi times the root of 1 plus 4x times 1 plus this expression squared, and that expression squared gives you 4 over 1 plus 4x dx. And like the previous example, we find a common denominator inside that second. So 1 to 5, 2 pi root 1 plus 4x times the root of 1 plus 4x plus 4 over 1 plus 4x dx. And just like in the previous example, this will cancel with that, leaving us with the surface area equaling 2 pi times the integral from 1 to 5 square root of 5 plus 4x dx. Now let's continue by antidifferentiating the square root of 5 plus 4x. So the antiderivative of 5 plus 4x will be 5 plus 4x to the 3/2 power times 2/3. And to accommodate for that 4 inside of there, we will just have to insert a coefficient of 1/4 as well, evaluated from 1 to 5. And now canceling some stuff, that gives us pi over 3 times, now first we plug in 5 and we'll end up with 25 to the 3/2 minus, plugging in 1, we end up with 9 to the 3/2. Now 25 to the 3/2 is the square root of 25 cubed. So 25 rooted is 5, 5 to the 3rd is 125, minus the square root of 9 is 3, and 3 to the 3rd is 27. And in the end we have 98 pi over 3. Now for this next example, it is easiest to think of the surface area formula as S equals the integral from A to B, 2 pi r of x times the root of 1 plus f prime of x squared dx, where r of x is your radius. So here's what I mean. So we have 1 minus x squared between x equals 0 and x equals 1 is rotated at about the y-axis. So here is my curve. I am rotating this part about the y-axis. So because I have x values, it will be useful to keep the equations in terms of x. So because then my little distances I can find using this formula. So the only thing you have to figure out is what the radius is. What is the distance from the axis of rotation out to your little slice? And in this case, r of x is just equal to x. So for this example, my surface area is equal to the integral from 0 to 1, 2 pi x times the square root of 1 plus negative 2x squared dx, or the integral from 0 to 1, 2 pi x times the root of 1 plus 4x squared dx. Now here I think it's best to use a u substitution. So I'm going to let u equal 1 plus 4x squared. My du is 8x dx. So 1/8 du equals x dx. If I change my bounds, if x is equal to 0, then plugging that into this formula, I get that u is equal to 1. And if x is equal to 1, u is equal to 5. And this becomes the integral from 1 to 5, 2 2 pi times 1/8 u to the 1/2 du. Now that's pi quarters. Anti-differentiate u to the 1/2, and that's u to the 3/2 times 2/3 from 1 to 5. And when you work that all out, you end up with pi over 6 times 5 root 5 minus 1. In this example, we're going to rotate the curve y equals 1/4 x squared minus 1/2 ln x between x equals 1 and 2 about the y-axis, and we want to find the area of the resulting surface. So since it's rotation about the y-axis again, once again, we will have the radius equal to x. So we just need to find y prime. Y prime is equal to 1/2 x minus 1/2 times 1 over x. So the surface area will be an integral from 1 to 2 of 2 pi r, so 2 pi x, so the circumference times the length, which is the square root of 1 plus y prime squared. And when you square y prime, which is worked out on your notes if you would like to check your work, but when you square y prime, we end up with 1 plus x squared over 4 minus 1/2 plus 1 over 4x squared. And when you add, we have 2 pi times the integral from 1 to 2 x square root of x squared over 4 plus 1/2 plus 1 over 4x squared dx. So we have another one of those semi-tricky factor patterns where this is going to factor into the square root of x over 2 plus 1 over 2x, the quantity squared. And that allows you to take that square root. So you have 2 pi times the integral from 1 to 2, x times the quantity x over 2 plus 1 over 2x. Before we anti-differentiate, we distribute x. We have 2 pi times the integral from 1 to 2, 1/2 x squared plus 1/2 dx. To make the anti-differentiation a little bit easier, I'm going to take out that 1/2 and cancel it with the 2 pi, giving us pi times the integral from 1 to 2 of x squared plus 1 dx. It will just make your arithmetic significantly simpler. So now when we anti-differentiate, we have pi times 1/3 x cubed plus x, evaluated from 1 to 2. So first plugging in 2, we'll have pi times 8/3 plus 2 minus pi times 1/3 plus 1, which simplifies down to 10 pi over 3.